Hi, my name is Tim Nordeweer, and this is my final project for the Thayer School of Engineering at Dartmouth Professional Certificate in Applied Data Science program. And I'm going to talk today about predicting vacant land value through machine learning. For a bit more information on me, I've included a brief bio, which you can read by pausing the video here if you would like. I'd like to give you a high-level summary of this project and findings before I begin. The scope of this project was limited to Garland County, Arkansas, with the objective to identify and source data for features that offer significance in predicting transaction prices for vacant land. I performed various API calls and GIS queries to obtain a unique data set, which I then explored, transformed, and split into training and test sets. I found that several of the uniquely sourced variables were relevant and then used them as input variables for several supervised machine learning algorithms. The ordinary least squares model, or OLS model, minimized prediction error the best and is easy to explain, but two other machine learning models offered promise and deserve future study. So what makes up the real estate industry? The seller sets an asking price and a buyer makes an offer. And what the two parties agree on becomes the transaction price. But how does each party decide what to ask for or offer? Information is key. And when it comes to real estate, common sources include sites like Zillow or Redfin to get estimates. Or a real estate agent may provide MLS comps of recently completed transactions of similar type and time frame. You can see here that this information is often based on features such as the number of bedrooms, bathrooms, and dwellings. But what about vacant land? You can see that many of the metrics on Zillow for housing do not apply to vacant land. How should one consider pricing it? For housing, for commercial, farming? What if you're a business that relies solely on buying and selling vacant land? How should you determine value? You may have heard people say location, 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 but what makes a good location? What other features matter? Obtaining relevant features and using them to make predictions is the purpose of this project. I downloaded a Redfin dataset containing vacant land transactions in Garland County for the 5-year period ending in December 2020. You can see from the items circled in red that the dataset is missing a substantial amount of data, as was expected for vacant land. After removing the missing data, you'll see that there really are only a few pieces of information left, and those are price, lot size, latitude, and longitude. To add to the challenge, the distribution of transaction prices is highly skewed with some outliers and is also very concentrated at the low end. I'd like to introduce you to the data science problem-solving framework. First, I defined the technical problem, as we have just done after understanding the business problem. Then I obtain the data and select metrics that will define what a successful prediction model accomplishes. I pre-process the data by handling outliers and missing data through various cleaning techniques. Then I iteratively create and evaluate models on permutations of feature data, dummy variables, interactions, and transformations. As you can see from the green arrow, I limited this project scope to analyzing one full iteration of one data set. A future version of this project would consider redefining the technical problem and then using new data. My hypothesis for this project is that there are additional features beyond those just in the Redfin dataset that can explain some of the variation in price. The second part of the hypothesis is that a machine learning model can do a better job explaining that variation than solely relying on the mean and the standard deviation of all the transaction prices. This project followed the data science problem-solving framework and used this specific workflow, which included sourcing the data, exploratory data analysis, or EDA, pre-processing the data, machine learning, results and model selection, and then finally the conclusion. I'll go through all of this now. Here's a map showing the census tracts and block groups in Garland County. From the latitude and longitude coordinates, I used the Census Geocode API to determine the geography containing each data point in the Redfin dataset. I then called the Census Data API to populate the requested fields from tables in the American Community Survey. Data was available at the block group level, and you can see on the right which values were obtained. Those are median income, the total number of occupied dwelling units or households, the owner occupied rate, the poverty rate, median age, and the median household value. From the tax assessor's records, I extracted and binned parcel types into one of 4 categories, and those are residential, commercial, agricultural, or other. I also created 4 dummy variables based on confirmed vacancy or tax exemption status. From the USGS National Land Cover Database, I extracted the majority cover type by pixels within an approximate 400-foot radius of each parcel and binned them into one of 9 categories. You can see here this map shows a close-up view of the Lake Hamilton area, which is in Hot Springs in Garland County. This is a zoomed-in view to give you a sense of what the various pixel colors look like at a close view. From the FEMA flood hazard lines, I performed a GIS query to identify parcels that were in a flood hazard area, shown by the yellow dots on this map adjacent to the blue flood hazard lines. I converted the FEMA flood hazard lines into polygons and filtered by those greater than 6 million square meters, from which the distance in meters between the observation and the nearest body of water was computed. You can see from the shape of the water and other bodies of water in the county that there are an infinite number of ways that this step could have been performed. And there could be many arguments for or against certain size thresholds for this calculation. These lines correspond to the distances that were actually computed for each point. That brings us to the exploratory data analysis stage. Here is a scatter plot showing the location, price, and relative size of the properties in the data set. One observation I had when looking at this was that the lot sizes seem to be larger the further you are from Hot Springs. It's hard to tell, I know, because there are some data points in downtown Hot Springs that are very small, but you can go back to the previous maps and see that there are many points in downtown Hot Springs. And so this tells you that they do tend to be larger the further away you are. This plot depicts the composition of the data by land cover and land use. The important thing here is that there are some holes in the data richness, such that not every land cover intersects with each land use. In a bigger data set, you might see land use for each cover type. Ideally, there would not be any holes in the data. This plot shows the median transaction price normalized by lot size for each land use. The error bar in black corresponds to the 95th percent confidence interval. What's interesting here is that the residential properties seem to be worth more than the agricultural properties on a price per acre basis. Even the error bars are separated. I'm not going to spend too much time on this slide, but here's a plot of the initial feature correlations in the data set. Clearly, there's a benefit to developing a model that sorts out the influence across so many predictors. The goal for any model in this project was to maximize the accuracy of the predictions by minimizing the error between the predicted and the actual values. Because I wanted to avoid large prediction errors, I pay close attention to the root mean squared error, as it penalizes larger errors more. All else equal, higher R-squared values are better. For OLS models, the F statistic must be statistically significant. And the F statistic is essentially the ratio of the variance that's explained to the variance that's not explained by the model. The preliminary OLS models all follow the form of Y equals a bias plus a weight times a feature, and so on. I used these OLS regression models for preliminary assessment to narrow down which features, transformations, or interactions are important before using the more complex machine learning algorithms. One basic assumption of a linear model is that the residuals, or the prediction errors, are normally distributed. The highly skewed price distribution that I had previously showed contributed to initial models that had violated the basic assumption of linear regression, that the residuals are normally distributed. Taking the natural log transformation resolved this. You can see the price distribution here on the right after the transformation looks much more like a textbook example than it had before. In addition to the natural log transformation of transaction price, the lot size feature transformation was also found to be beneficial. Various feature interactions were tested, but none were statistically significant with both the lot size and the price transformed. From the preliminary OLS modeling, model number 22 performed the best. It had a root mean squared error of only $54,000 and an R squared of 40%. You can see on the left the typical QQ plot for a preliminary OLS model without the transformations previously described. The points shown in the model with normally distributed residuals would fall on the red line. The plot for model 22 with the transformations is on the right. I performed a Shapiro-Wilk test and confirmed that the residuals for OLS model 22 are in fact normally distributed. The features in the model serve as a baseline for understanding what features may be important in machine learning. These features are highlighted in the green box on the right. Finally, before I applied any machine learning algorithms, I one-hot encoded categoricals with dummy variables, split data into training and test sets for k-fold cross-validation, and prepared a normalized and standardized feature set. I started with features identified from OLS Model 22, but I wanted to allow the machine learning algorithms the opportunity to use additional inputs such as latitude and longitude. I used the three feature sets to iteratively run machine learning algorithms using a grid search strategy, tuning hyperparameters for each algorithm. For this presentation, I don't have time to cover the inner workings of each algorithm, but at a surface level, the Lasso linear regression basically adds a penalty term to the regular linear regression for large coefficients. Decision trees are very good at breaking down the data along groupings, though they sometimes overfit. Gradient boosting regression relies on creating many internal models that each reduce the prediction error slightly. Support vector regression tries to make an equation similar to the y equals mx plus b form, but it warps variable space using a kernel trick to establish a hyperplane for drawing the line of regression. Finally, a random forest essentially makes many decision trees and outputs the mean as the final answer. It tends to avoid overgeneralizing and is a powerful ensemble model. When looking at the results from various permutations of algorithms, features, and hyperparameters, it is clear that the support vector regressor underfit the data and that the gradient boosted model with a maximum depth of 7 overfit the data by not generalizing well to the test sets. This is evidenced by the reported R squared of 99%, but an R squared of only 17% for the data unseen by the model through k-fold cross-validation. The random forest and a different gradient boost model both did a good job fitting the data and maintaining adaptability across random sets. They had reasonable k-fold R squared values. In the end, OLS model number 22, which is technically a log linear model, had the best R squared of 40% and the lowest root mean squared error, making it not only the best performer, but also the easiest to explain. Here's the final model, unpacked. To use the model, one needs to know the features used as inputs. The predicted transaction price is the exponential function of the standard regression equation since the price was transformed in the model. And you can see that over here where price equals E raised to the typical regression equation. In conclusion, statistical features were in fact identified from external sources beyond the Redfin dataset, and the final selected model had a root mean squared error of $54,000, which is less than half of the standard deviation in price of about $114,000. So we do have evidence that supports both parts of the hypothesis. This model, the final model, would give a developer a competitive edge in setting asking or determining offer prices in the Garland County vacant land real estate market. Future iterations of this project, in future iterations, I would try to get more data. I would test other ways of calculating that distance to the bodies of water that I had alluded to previously. I would test out other machine learning algorithms and different hyperparameters for the ones that were tested. And I would adjust the transaction prices for inflation. Unfortunately, the Redfin data did not have a complete set of time series information for each observation. That concludes my presentation today. Thank you very much for watching. I appreciate your time, and I hope that you enjoyed.